Welcome to the deep dive. Today, we're diving headfirst into transhumanism.
Hmm.
This powerful idea of using technology, biotech, AI, all of it, to fundamentally upgrade the human experience.
Yeah, it's huge.
We're not just talking treating illness, but really pushing the boundaries of what our bodies and minds can actually do. It's a wild ride, interdisciplinary, packed with, well, incredible possibilities and some really naughty ethical questions.
Absolutely. And for this deep dive, the sources you pulled together are fascinating. We're looking at the core technologies driving this gene editing, mind-machine connections, that sort of thing.
Right.
But crucially, we're also digging into the ethics that come with such, well, profound power. We're even looking back at the CIA's M-Culture program for context.
Exactly.
Yeah.
Understanding the meaning behind it all.
Yeah, what it truly means for us.
Exactly. So, listener, our mission today is to cut through the complexity, get right to the heart of what you need to know about these game-changing technologies.
Hmm.
We want you to grasp their potential impact on your life, on society, and really get a handle on the big ethical debates they spark.
Kind of like your informed guides through this exciting, maybe slightly overwhelming territory.
Precisely. Okay, let's unpack this. Starting with biology itself, how we're fundamentally changing it through genetic and cellular engineering.
Yeah, the pace is just striking. Take CRISPR technology.
Okay.
It's a revolutionary gene editing tool. Think of it like super precise molecular scissors,
Right.
guided by a specific address that's the guide RNA to cut DNA exactly where you want it, using the Cas9 protein.
And this came from bacteria.
Yeah, interestingly, it's their defense mechanism against viruses originally. But what made CRISPR such a game changer was its, well, relative simplicity, low cost, and just incredible efficiency. It blew the doors open for scientific breakthroughs.
And it's moving so fast, isn't it? The advancements sound like pure science fiction sometimes.
Totally.
These even more accurate versions of the scissors nick Cas9, dead Cas9, reducing unwanted edits.
Precisely. They make fewer mistakes, basically.
Yeah.
And then you got base editing. That's another big step. It lets you make very specific changes, like swapping one DNA letter for another without making those riskier double-strand breaks in the DNA.
Oh, okay. Less collateral damage.
Exactly. And prime editing, that's even more sophisticated. It uses a modified Cas9, a special guide RNA. It's got the potential to correct like almost 90% of known human genetic mutations.
Wow.
Single letter changes, small insertions, deletions. It's an incredibly versatile toolkit.
And it's not just limited to DNA, right? I read about RNA editing too.
That's right. Using Cas13b, it's like making a temporary edit to the messenger molecule, the RNA, not the permanent DNA blueprint.
Which could be safer for certain things.
Potentially, yeah.
Right.
Less permit commitment. And there's even a smaller CRISPR enzyme now, AsCas12. It's tiny, about a third the size of the original Cas9, but just as effective.
Easier to deliver into the body, I guess.
Exactly. Fits better into those delivery vehicles like AAV vectors.
Okay, so here's the big question. What does all this mean for us beyond just fixing diseases? This is where it gets really interesting.
Right. If you zoom out, the potential for enhancing human capabilities, not just treating illness, is, well, pretty remarkable.
Mm-hmm.
We're already seeing promising results in trials using CRISPR for things like sickle cell anemia, beta thalassemia, correcting the root genetic cause.
Yeah, I saw some headlines on that.
And researchers are looking at it for cystic fibrosis, Duchenne muscular dystrophy, even inherited blindness, neurological disorders.
Yeah.
The list is growing.
Okay.
But looking further out, the sources suggest potential for, say, extending our healthy lifespans by targeting aging-related genes.
Really? Tinkering with aging itself?
That's the idea.
Yeah.
Or even potentially enhancing cognitive function by modifying genes linked to how our brains work. It really paints a picture of humans, taking the reins of their own biology.
It's almost hard to wrap your head around. And then, sort of alongside this, we have regenerative medicine, another huge piece of this future puzzle. It's all about creating new living tissues to repair or replace damage, right? From aging, disease, injury.
Exactly. The goal is to harness the body's own healing powers. And that's crucial, given the constant shortage of organ donors.
And stem cells are key here.
Absolutely central. Stem cells are unique because they can develop into many different cell types. Scientists use them to understand diseases better, grow healthy cells for transplants, even test new drugs.
What kinds of conditions are we talking about?
Leukemia, lymphoma, type 1 diabetes, Parkinson's, ALS, heart failure, osteoarthritis. I mean, these are just some areas where stem cell therapies are being actively explored.
And it's not just individual cells anymore, is it? We're talking tissue engineering, even 3D bioprinting. like
Yeah,
actually building organs.
precisely.
Yeah.
The progress there is aiming to create functional bioartificial organs. The dream is to end transplant waiting lists and offer totally personalized solutions. There's also a lot of research into aging, like regrowing muscle tissue lost with age. And cell sheet engineering is another cool technique, growing layers of cells without a scaffold, showing promise for repairing hearts, skin, corneas.
So regenerative medicine isn't just about fixing what's broken, it's about potentially pushing past our natural limits, slowing decline, extending health span, making us stronger.
That's definitely part of the vision. Mitigating or reversing age-related decline, extending not just lifespan but health span, increasing strength, enhancing overall physiological performance. It's about going beyond restoration.
Now, what happens when you combine the pinpoint accuracy of CRISPR with the rebuilding power of regenerative medicine? That sounds potent.
Yeah, that synergy is really interesting. Combining them ramps up the potential significantly. For instance, you could use CRISPR to make stem cells even better at regenerating tissue.
Like supercharging them.
Kind of, or crucially, making them compatible with a patient's immune system. That's a huge hurdle for things like diabetes treatment, using donor cells editing the immune markers.
Ah, avoiding rejection.
Exactly. And what's really exciting is the idea of personalized regenerative treatments. Take a patient's own cells, use CRISPR to fix a defect or add a beneficial tweak,
Right.
and then use those edited cells to regenerate tissue or even grow an organ specifically for them.
Super targeted. Tailor-made repairs.
It's incredibly targeted. A level of customization we just haven't had before.
Okay, so we've covered the biological level, genes, cells, tissues. Let's zoom in even further now to the nanoscale frontier. Nanotechnology in medicine. Tiny tech, huge potential, right?
Yeah.
Especially for cell repair.
Yeah, what's fascinating here is working at the level of atoms and molecules. Nanotech gives us this incredible toolkit for diagnosis and treatment with unprecedented precision.
Fixing things at the molecular level.
Exactly. That's the focus. Repairing cells directly.
Hmm.
Research is already showing that nanomaterials, even tiny nanorobots, could potentially fix damaged cells.
Like what kind of fixes?
Well, one example is delivering corrective proteins via nanoparticles to mend faulty brain circuits. They've shown promise in animal models and human tissue for things like neurodegenerative diseases or intellectual disabilities, regrowing neural networks.
It sounds like it could make traditional drugs almost obsolete eventually. These tiny machines doing complex medical jobs.
That's the long-term vision, yeah. Nanorobots augmenting or even bypassing our natural healing, directly repairing cells and tissues, medicine freed from just relying on innate healing.
Tiny toolkits swimming in our bloodstream.
Basically, introduced, maybe guided by surgeons, programmed to find the molecular roots of diseases like Alzheimer's or Parkinson's and perform intracellular surgery.
Wow.
It means directly tackling damage at the source, potentially reversing diseases or injuries once thought irreversible.
Truly groundbreaking. And nanotech isn't just fixing, it's also changing drug delivery, right? Making it much more targeted.
Absolutely. Nanoparticle drug delivery systems allow for incredibly precise targeting and controlled release.
So fewer side effects.
Exactly. Get the drug right where it's needed. Minimize impact elsewhere. Nanomaterials can also improve drug stability, solubility, how easily they get into cells, how long they last in the body.
And there are different types of these nanoparticles.
Yeah, polymeric ones, lipid-based ones like liposomes, inorganic, even biological ones, lots of variety.
Different ways to get them to the target. I heard about passive targeting for tumors.
Right, the EPR effect. Basically, leaky blood vessels in tumors trap nanoparticles. It's useful, but passive.
Okay.
Active targeting is more precise. You attach specific molecules, ligands like antibodies or peptides, to the nanoparticle surface.
Like little homing beacons.
Yeah, exactly. They bind to receptors on the target cells, helping the drug get inside and accumulate in diseased tissues, not healthy ones. Reduces toxicity.
And this could help with getting drugs into the brain, across the blood-brain barrier.
That's a huge potential application, yes. A major challenge for CNS disorders. Nanotech could open doors not just for treating neurological diseases, but maybe even future cognitive enhancements. The market growth predictions for nanodrug delivery are pretty significant.
And nanotech is also weaving into regenerative medicine, the field we just discussed.
Definitely playing a crucial role there, too. It provides sophisticated tools and materials to really boost tissue regeneration and stem cell therapies.
How so?
Well, you can use nanomaterials to build scaffolds that mimic the natural environment around cells, the extracellular matrix.
Ah, giving the cells the right support structure.
Precisely. providing support, but also cues to guide stem cell growth and specialization. They're using this approach for skin, cartilage, bone, nerve, even heart tissue regeneration.
It's like creating the perfect little neighborhood for cells to rebuild in.
That's a good way to put it. And you can even integrate nanocomponents into the stem cells themselves.
Really? Inside the cells?
Yeah, to study their internal signaling, create even better conditions for regeneration. Metal-based nanoparticles, gold, silver, are getting a lot of attention for influencing stem cell fate, guiding differentiation.
And for tracking them too, seeing where they go.
Yes, tracking and imaging. So combining nanotech with stem cells really pushes towards precision medicine in regeneration. Unprecedented control over cell behavior for personalized, effective treatments.
Okay, so we're manipulating life down to the nanoscale. Now let's shift gears to merging mind and machine, AI and cybernetics. Starting with AI-powered prosthetics, these are way beyond simple replacements now, aren't they?
Oh, absolutely. AI is transforming prosthetics into intelligent systems. They feel and function much more like natural extensions of the body. Huge leaps in control, responsiveness, user experience.
How does the AI help with control?
Well, AI algorithms can interpret the subtle nerve signals from a patient's remaining muscles much better. This allows for finer, more intuitive control, especially with myoelectric prosthetics that use those muscle signals, EMG.
We're seeing things like bionic legs that adapt to the environment, like that one from Utah.
Exactly. Using AI and feedback, those legs learn to handle obstacles, uneven ground, stairs. They adapt. And prosthetic arms with AI and computer vision, like the Newcastle University one from a few years back,
Yeah.
they can actually see an object, identify it, and adjust the grip automatically. It's moving towards the prosthetic, anticipating the user's needs.
Less conscious effort required from the user.
Right. And the cutting edge is direct neural interfaces,
Yeah.
connecting the prosthetic directly to the nervous system.
Like the MIT Brigham in women's research,
Yeah.
getting a natural walking gait.
That's a prime example. A prosthetic leg fully driven by the nervous system via a new surgical approach and interface. That's truly seamless integration, a real game changer.
And it's not just replacing limbs, we've also got robotic exoskeletons augmenting existing abilities.
Absolutely. Wearable mechanical devices to boost strength, mobility, for injury prevention, lifting heavy loads, improving mobility for those who need it.
They come in different forms, lower body, upper body.
Yeah, lower, upper, full body, depending on the application.
And AI is helping develop these too. I saw something about training them to save energy.
Yes, the North Carolina State University work, using AI and simulations to train exoskeletons to automatically help users walk, run, climb stairs more efficiently. The suit learns how to assist optimally, reducing the user's metabolic energy cost.
Without the user having to train it extensively.
Exactly. It learns autonomously.
And we're seeing these exoskeletons pop up everywhere, healthcare industry, even space.
That's right. Healthcare for rehab and mobility assistance. Industry and defense for supporting workers, reducing fatigue, enhancing strength, things like the HAL exoskeleton, and NASA's X-1 for astronaut health and potentially helping paraplegics.
So these AI prosthetics and exoskeletons, they really embody cybernetics, don't they? This human-machine integration.
Precisely. They create these closed-loop interactions.
Yeah.
Human input leads to tech response, user gets feedback, the system learns and adapts. It becomes a more integrated functional relationship.
It's more than just replacement or addition.
It really is. It's a step towards seamless, intuitive integration, pushing physical boundaries and potentially cognitive ones too, especially as those neural interfaces get better and better.
Okay, now let's tackle what many find the most fascinating, maybe even unsettling area. Decoding the brain with brain-computer interfaces, or BCIs. How do these actually work?
Well, at their core, BCIs create a direct communication link between brain activity, specifically electrical activity, and an external device, a computer, a robotic limb, whatever.
Bypassing the usual nerve and muscle pathways.
Exactly. Theoretically, you could use any brain signal, but most common are electrical signals measured in a few ways. Electrodes on the scalp, that's EEG.
Non-invasive.
Right, or implanted in the brain tissue, that's intracortical.
Invasive.
Fair. Or just on the brain surface, called ECOG.
So you're basically listening to the brain's electrical chatter.
In a sense, yes. The process has key stages. First, signal acquisition recording those signals. Then, feature extraction algorithms identify patterns linked to what the user intends to do, like changes in brainwave strength or neuron firing rates.
Okay.
Next is feature translation, converting those patterns into commands for the device. Move a cursor, flex a robotic finger.
Got it.
And finally, device output. The device does the thing, and crucially provides feedback to the user. That closes the control loop, helps them learn.
And AI and machine learning must be absolutely critical here to make sense of all that complex brain data.
Oh, completely essential. AI deciphers those incredibly complex neural patterns and adapts as brain signals change over time. The BCI learns the user's specific brain language for intentions, leading to much more accurate control.
And we've seen some really striking progress recently, both invasive and non-invasive.
Huge progress. Invasive BCIs, the implanted ones, are showing amazing potential for restoring function, like the UC Davis Health BCI, translating brain signals to speech for an ALF patient with really high accuracy.
Correct.
And then you have companies like Neuralink doing human trials now, enabling cursor control, robotic arm control via thought. And BlackRock Neurotech, they've been pioneers with their Utah array system in research for years.
Right. And what about non-invasive? Still lagging behind or catching up?
Catching up significantly, actually, thanks to AI and better signal processing. Johns Hopkins APL had that breakthrough using holographic imaging to record neural activity non-invasively with high resolution.
Interesting.
And Meta AI's system, Brain 2 QWERTY, using MEG, which measures magnetic fields, to decode imagined speech. It's getting surprisingly close to invasive methods in accuracy.
Wow.
Plus, we're seeing more consumer-grade non-invasive BCIs for focus, productivity, even mental health applications like depression, using headsets.
Neuralink has been all over the news. Can you give us the latest updates there? What's happened in 2024, 2025?
Yeah, Neuralink has definitely kept moving. They did their first human implant, the Link, in January 2024. Nolan Arbaugh, who has
Oh, I
paralysis.
saw that. He was playing games, browsing online. Yeah.
Exactly. Controlling a cursor, live streaming, all with thought. Since then, reports say they've implanted at least 2 more individuals, Alex and Brad, also with paralysis, and collectively, they're using this telepathy system for hours every day.
And they're aiming beyond just cursor control, right?
Mhm.
Robotic arms,
Oh.
vision.
Absolutely. They got approval for a study called CONZY, testing the N1 implant to control an assistive robotic arm.
Ah,
There was that video demo early this year, 2025, showing a patient controlling a robotic arm to write convoy just by thinking. Pretty compelling.
definitely. And blind sight, restoring vision.
That's their initiative for blind individuals who still have an intact visual cortex. It's got a breakthrough designation from regulators,
Yeah.
suggesting high potential. But they're clear. Several testing rounds are needed before wider access.
Sounds incredibly promising. But there's been controversy, too. Ethical concerns.
That's definitely part of the conversation.
Yeah.
Scrutiny over their animal testing history, questions about long-term safety of implants. These are ongoing discussions. Elon Musk has talked about a potential future cost, similar to LASIK, maybe $5,000, with a quick robotic implantation. But, it's still very early days.
Yeah.
It needs long-term data, rigorous evaluation.
Right, of course. Now, DARPA, the U.S. Defense Research Agency, they've also been pushing BCI tech hard with their N3 program. What's their angle?
DARPA's N3 program, Next Generation Non-Surgical Neurotechnology, is really interesting.
Yeah.
Launched in 2018, the goal is high-performance, bidirectional BMIs for able-bodied service members, but without surgery.
No surgery. For military applications.
That's the aim. National security applications. They're exploring optics, acoustics, electromagnetics, ways to read from and write to the brain with high speed and resolution, all non-surgically.
So completely external systems.
That's one research track, yes. Completely non-invasive external devices. The other track is minutely invasive, using tiny nanotransducers delivered temporarily and non-surgically to boost signal quality.
Nanotransducers. How would they work?
One team, Battelle, is working on electromagnetic nanotransducers that convert the brain's electrical signals into magnetic ones, which are easier to detect externally. And they aim for two-way communication. Other teams are using light and sound, or just light and magnetic fields. Rice University is even working on a headset for direct brain-to-brain communication without surgery.
Brain to brain. Wow. What are the biggest hurdles they face?
Well, the skull and skin scatter and weaken signals significantly. That's a major physics challenge. And designing algorithms to accurately decode and encode neural signals non-invasively is incredibly complex.
What's their performance target?
The goal is precision. Yeah. Reading from and writing to 16 independent channels within a tiny brain area very quickly. It's ambitious.
And they've considered the ethics.
Yes. Importantly, they involved independent legal and ethical experts from the start, considering both military and potential civilian implications. If N3 succeeds, it could make high-performance BCIs much more accessible by removing the need for surgery.
Okay, we've seen the amazing potential. But to really understand the risks, the ethical minefield, we need that historical perspective. Let's talk about the CIA's M-Culture program. What was that actually about?
And Culture was a deeply secret CIA human experimentation program.
Mm.
It ran mainly from the mid-50s to early 70s Cold War era.
Right.
It stemmed from U.S. fears that the Soviets, Chinese, North Koreans were developing mind control techniques they thought POWs in Korea had been subjected to it.
So they wanted their own.
Primarily, the goal was developing interrogation techniques, finding drugs, methods to weaken people, force confessions via brainwashing, psychological torture. But secondarily, yeah, they explored mind control for offense, manipulating leaders, discrediting people.
And the methods, they were disturbing, unethical.
Profoundly so. A huge understatement. They covertly gave psychoactive drugs, especially LSD, to thousands of people.
Without consent.
Often without any knowledge or consent. In universities, hospitals, prisons, often disguised as research. They also heavily studied hypnosis, psychological manipulation for control, sensory deprivation, isolation, trying to break people down mentally.
It wasn't just LSD, though, was it?
No. They tested barbiturates, amphetamines, heroin, morphine, mescaline, psilocybin, scopolamine, marijuana, alcohol, sometimes in combination, even explored chemical, biological, radiological agents.
Good grief.
And historical accounts, declassified bits, suggest electroshock, verbal and sexual abuse. Other forms of torture were used in some experiments, all non-consensual.
They even had specific goals written down.
Yeah, a 55 document mentioned developing drugs to make people think illogically, act impulsively, enhance perception, counteract alcohol, cause amnesia, make hypnosis easier. I mean, it's chilling.
It's horrifying, and we don't even know the full extent because records were destroyed.
That's right. The CIA director ordered most M-Culture files destroyed in '73. So investigations later, like the Church Committee, had to rely on testimony surviving fragments.
But what we do know is bad enough.
Oh, absolutely. It revealed a program far bigger and more disturbing than first thought, involving at least 86 institutions. Exposed countless ethical violations, human rights abuses, just deeply abusive.
And did it influence later interrogation techniques?
Evidence suggests some techniques explored might have trickled down, yes. Used later by the U.S. and allies.
Yeah.
Ultimately, M-Culture is this stark reminder of how government research can go horribly wrong, cross fundamental lines, cause immense harm.
Which really highlights the need for transparency, consent, oversight, especially with mind-altering tech.
Critically important lessons, especially now.
Definitely. Which brings us squarely to the ethical dilemmas of today's technologies. Starting with genetic and cellular engineering. CRISPR is amazing, but the ethics.
Huge debates. Big concerns about off-target effects, accidentally editing the wrong part of DNA, causing harm.
Right.
And germline editing changes past to future generations that's profoundly ethically charged. What are the long-term consequences for the human gene pool? We just don't know.
And the therapy versus enhancement line?
Exactly. Most agree using it for therapy, fixing diseases is good. But using it to enhance baseline abilities, intelligence, strength, much more contentious. Some call it a dangerous Promethean aspiration to remake human nature.
There's also the fairness issue, right?
Yeah.
Exacerbating inequality.
A critical concern. If only the rich can afford enhancements, does it create a biological divide? Widen the gap between haves and have-nots?
Although some argue enhancements might level the playing field.
There are counter-arguments, yes.
Yeah.
That cognitive boosts might help bridge gaps, or that we already use enhancements that blur lines. But it's a major ethical debate. And fundamentally, it forces us to ask, what is human? Could radical changes make us unrecognizable?
Nanotechnology in medicine, too, despite its promise, raises ethical flags.
Definitely. Consent and privacy are big ones. If nano devices inside you can collect physiological data, who owns it? How is it used? Plus, we don't fully know the long-term effects of nanomaterials in the body. Potential toxicity, unforeseen consequences down the line.
And nanorobots operating inside cells. Control becomes an issue.
Very complex ethical challenges there. Control over autonomous or semi-autonomous machines inside you, potential for intrusive monitoring, intervention, and the therapy enhancement debate pops up again. Repairing cells is one thing. Nano implants for sensory or cognitive boosts. That pushes fundamental questions about naturalness, fairness, altering human nature at the micro level.
Moving to AI and cybernetics in augmentation, advanced prosthetics, exoskeletons. New ethical wrinkles there, too.
Yes, definitely. User autonomy is a big one. How much control does the user really have when the device is AI-driven? What about dependence, relying on tech for basic or enhanced functions?
And identity. Where does the human end and the machine begin?
Exactly. Deep philosophical questions, plus major societal impacts. Employment, unfair advantages for the augmented. discrimination against the unaugmented.
And a cost. Social equity.
Huge issue. High costs could create a divide, worsen inequalities. And how does it change how society views disability? What becomes normal or desirable function? Plus, you've got algorithmic bias in the AI itself and the need for strict regulation for safety and responsible use.
And finally, BCIs. Direct brain connection. Arguably the most profound ethical challenges.
You're absolutely right. Mental privacy is paramount here. The potential to access, record thoughts, emotions, intentions, it's huge.
Who owns that brain data? How is it protected?
Critical questions. We need robust privacy frameworks to stop misuse. And then there's cognitive liberty, the right to control your own mental states without coercion.
BCIs challenge that directly.
They absolutely could. Concerns about external influence on brain activity, subtle or overt manipulation, erosion of autonomy, free will, these are significant. Informed consent is also tricky. The tech evolves so fast, unforeseen consequences are possible. People need to fully grasp the risks, especially vulnerable groups.
And the therapeutic versus enhancement uses again.
Raises all those questions about fairness, societal impact, redefining human normality if cognitive enhancement becomes widespread.
This intersection of enhancement and control really circles back to M-culture, doesn't it? Its lessons feel incredibly relevant now.
It really does. M-culture is that chilling precedent for misusing mind-altering tech. All that non-consensual experimentation with drugs, hypnosis, manipulation, aiming for mind control and behavior modification.
A total ethical failure.
Resulting in severe human rights violations, lasting trauma. And while today's neurotech is way more sophisticated, M-culture shows the enduring, dangerous interest in controlling minds.
Underscoring the need for strict ethics and oversight now.
Absolutely critical. The secrecy, the destroyed records, the harm caused their cautionary tales for navigating transhumanist tech today, especially neurotechnology and anything touching mind control.
And the future possibilities for mind control given advanced BCIs and AI. That's a serious concern, isn't it?
It is, yes. BCIs, while potentially beneficial, could be exploited, subtly or overtly controlling thoughts, emotions, behaviors. AI algorithms analyzing brain signals could target neural activity linked to specific thoughts or emotions, allowing external influence, maybe even subliminally.
For political aims, national security.
Those are the kinds of concerns raised. Influencing voting, exploiting the nervous system, AI convergence amplifies the risk, enabling analysis of vast brain data to find vulnerabilities, develop manipulation methods.
Even non-invasive tech like DARPA's N3 raises concerns.
If safeguards aren't incredibly robust, yes. Potential for widespread, undetectable manipulation is a worry.
It's that strange paradox you mentioned, transhumanism, aiming for individual autonomy but potentially creating vulnerabilities to control.
Exactly, a paradox we have to actively confront. The push for deeper human tech integration could, without ironclad ethics and security, undermine the very cognitive sovereignty it claims to enhance.
So the vision needs careful balancing.
With robust safeguards against eroding autonomy. M-culture reminds us, the quest for enhancement must prioritize individual rights and freedoms, especially concerning the mind.
So, given all these huge ethical challenges, what's being done? Are there initiatives trying to govern this, create ethical frameworks?
Yes, thankfully there's growing international recognition of the need. UNESCO, for instance, is leading a major global effort developing the first ever recommendation on the ethics of neurotechnology.
Involving all member states.
All 194, yeah. Aiming for a shared framework, values, principles, policy actions to guide neurotech development and use. The focus is heavily on safeguarding brain integrity, human dignity.
What are the key points they're hitting?
Preserving personal identity and psychological continuity as we interface with tech. Ensuring individuals control decision-influencing neurotech. Identifying rights at risk, autonomy, freedom of thought, cognitive liberty, free will.
Mental privacy, too.
Absolutely. Mental privacy, brain data confidentiality are central. And considering how neurotech might worsen social inequalities.
And when might this recommendation be finalized?
They had expert drafts, consultations. An intergovernmental meeting is planned for spring 2025, with final adoption hoped for at UNESCO's General Conference in November 2025. It shows a growing global consensus on needing governance to balance progress with rights.
That sounds promising. What about specific regions, like the EU?
The EU is very active too. The concept of neuro rights is gaining a lot of traction there.
Neuro rights, what does that mean?
Basically, ethical, legal, social principles, specifically for the brain and mind, aiming to protect brain activity from misuse. Several specific rights have been proposed.
Such as
Things like The right to mental privacy consent for brain data use, no selling it. Right to personal identity limiting tech that fundamentally alters self. Right to free will protecting against neural manipulation. Right to equal access to mental augmentation regulating to prevent inequality. And protection from algorithmic bias based on brain data.
So they're debating if current human rights laws cover this or if new specific neuro rights are needed.
Exactly. Maybe a formal declaration on neuro rights. They're also looking at tech-specific risk evaluations, tracking public discussion, funding research, supporting EU providers, data security. The Council of Europe also has neurotech in its action plan on biomedicine.
Are there other players involved? OECD. Nonprofits.
Yes, the OECD had a recommendation on responsible innovation in neurotechnology back in 2019, the first international standard. Academic institutions, nonprofits like the Neuro Rights Foundation are doing crucial research, advocacy, public awareness, and industry groups are starting to develop their own guidelines and best practices.
So there's a growing recognition that we need to get ahead of this.
Definitely. A proactive approach to the ethical and societal challenges is emerging, especially for brain interfacing tech.
Okay, so wrapping up this deep dive, what are the main takeaways about the future of transhumanity? It feels like this incredible knife edge of promise and peril.
That sums it up well. We've seen these amazing scientific leaps, CRISPR, regenerative medicine, nanotech, AI cybernetics, BCIs. They truly could fundamentally alter the human experience.
Right.
But as we've hammered home, each comes with massive ethical baggage. Off-target edits, germline changes, inequality, nanomedicine privacy, long-term effects, AI autonomy, dependence, human-machine blurring, BCI privacy, liberty, manipulation potential, all underscored by historical warnings like MKUltra.
And the trend is towards more convergence, biology and tech blurring.
Increasingly so. Rapid advances will likely continue. Technologies will synergize more CRISPR with stem cells, nanotech with gene editing, AI underpinning everything.
Leading to optimistic scenarios or
Yeah.
pessimistic ones?
Exactly. Disease eradication, longer health spans, enhanced abilities on one side, increased inequality, lost autonomy, misused for control on the other. Timelines are hard to predict, but transformative applications seem likely in the coming decades.
So responsible development is crucial.
Absolutely essential. Careful thought about ethical frameworks, governance like the UNESCO and EU initiatives. Continued public discussion is vital. People need to understand the benefits and risks.
Balancing innovation with protecting rights.
That's the tightrope we have to walk. Protecting rights, dignity, autonomy. We need regulations, oversight to prevent misuse, ensure fair access. The future of transhumanity really depends on navigating this ethical maze wisely, with human well-being and respect for life as our compass.
And on that profound note, listener, I leave you with this final thought. Reflect on which specific aspect of the transhumanist technologies we've discussed today you believe presents the most significant ethical challenge for humanity, and what core principles should guide our decisions as we continue to venture into this uncharted territory. Thank you for joining us for this deep dive.